Okay, so let's hit your review. Again, it's using your same pieces here. As x, this is what we're looking for. As x approaches infinity, we have 3 rules. So take out your sheet with your 3 rules. It says, look at your highest exponent in the numerator, which is x squared, your highest exponent in the denominator, which is 4x squared. If they are equal, then make a ratio of their coefficients. Normally, your horizontal asymptote would say y equals 1/4. This was our horizontal asymptote. But because we're saying limit, all we have to do is say it equals 1/4. As x approaches infinity, the y value is going to approach 1/4. If I could make it hit that point, it would have to hit the 1/4. It's going to get so darn close to it. Same as our point of discontinuity. It gets so close to it from both ends, we could fill it in. I kind of scattered these around. This is as x approaches 0, not infinity. So we always try to substitute in first. So we try to substitute the 0 in. And what happens? You can't use a 0 in the denominator, right? So therefore, we know we have to eliminate that somehow. There's no way right now we can pull that x out of the radical. So this one has to be rationalized. So we rationalize top and bottom with its conjugate. This was something a little new that we did. We used to rationalize your denominator. This time we had to rationalize your numerator. So this comes out, this comes out. Slide this over. Don't distribute it, because your goal is to factor this out. It'll reduce out. And then we can take out the x, common factor, and even though we're left with something that's not so pretty, we can now substitute in the 0. And if you graph this again, you'll see that that's a little point that we can eventually fill in. If we could find its y value, it would be 1/2. If we looked at it from the left and the right, it would merge to the 1/2. Always try doing a direct substitution. If you don't have this, you should be writing this down. This is your review. Once we finish your review, this is what you're going to review for your final. So we say, what is the limit as x approaches -3? I plug a -3 in here, and I say, whoops, it gives me a 0. So I must have to somehow get the x plus 3 out of there. So it's a factor. So I'm going to factor and reduce. What I factor out, remember, is called your point of discontinuity. So when you reduce this down, this is the reduced function, I now can substitute in the -3. And I could find the value of my limit as x approaches -3. If I could just fill in that point, I would have -3, -5. That would be my point of discontinuity. So my limit is what y value that I would be able to fill that in with. This one, we substitute in -3. It says, whoops, can't do it. So we try to factor and reduce, and we can't. So I get a little confused, so I graph it, and I notice, oh, well, if I can't factor and reduce, this guy was a vertical asymptote. And a vertical asymptote makes my end behaviors not me. They go off in different directions. It's something that I can't pass through. You can never pass through a vertical asymptote. So here's my end behaviors going in different directions. This limit does not exist. When you find something like that, it doesn't mean you're wrong. Doesn't mean you should still keep trying to factor it because you couldn't. Graph it and see what it looks like. And you'll see that, yeah, I couldn't graph that. I couldn't see those meet at any point. And it turns out that that's your vertical asymptote. Okay. Again, this guy, first thing I do is direct substitution. I try to substitute in the 3. And, oh, that lets me do it. So I substitute in 3. Now, as I approach 3, I can have an exact point. That is still my limit. It is there. And my point would be negative 1/2. So my limit is equal to negative 1/2. This one I thought we would do together. I thought we would do this one together. Because this one, we did your rational functions back probably like October, November. So I was kind of hoping that if we tie this together and then we look at it as a limit, it might actually make sense. So let's make sure we do this one together. All right. So tell me everything. So first tell me, do I have a domain restriction? Is a fraction necessarily giving a domain restriction? Yeah. Because I have a variable in my denominator. And that variable, whatever I put in there, cannot cause that to go to 0. So I say, oh, let me set this equal to 0. I have to factor. So x cannot be negative 3 or positive 2. Agree? But that'll make this thing go to 0. Won't work. So my domain says, okay, we go from negative infinity to negative 3, jump over negative 3, go to 2, jump over 2, and use anything else you feel like it. Now, because I factored this, it also helps me reduce this. Because now, before I find anything else, I have to reduce. What factor do I have in the numerator and the denominator? X plus 3. If I take this out, this is my point of discontinuity. So x plus 3, when x is negative 3, I have a removable point of discontinuity. Look what remains, 1 over x minus 2. This x minus 2 gives me a vertical asymptote. Remember doing these? Very similar, right? Then we said, oh, well, you must also have a horizontal asymptote. My degree in the numerator is less than my degree in the denominator. What's my horizontal asymptote? 0, right? Equals 0. So if I wanted to sketch this, I would start like this. I would start my asymptote. I've got a y equals 0. I've got an x equals 2. Okay? I have a removable point at negative 3. So when I put this guy in my calculator and I sketch this, I find that it looks like this. And it looks like I'm filling in my negative 3, but that's really where my point of discontinuity is. So now let's relate this for a second to your limits. As this function, as x approaches negative 3, I'm approaching negative 3 from here and here. Will I approach the same point? Will it come meet? Yes. So all I need to do is find this point. So I take my negative 3 and I plug it into my reduced function. I plug in my negative 3 because I couldn't do it to the beginning. So I got 1 over negative 3 minus 2. I got negative 1/5. There's my limit. My point of discontinuity is negative 3, negative 1/5. If I could just fill that little point in, that's what it would be. But my limit itself is just negative 1/5. As I approach the value of 2, x is 2. Here's x is 2 over here. What happens at x is 2? Do I approach the same point? No. It pushes it in different directions. This limit does not exist.
That's the jump, right?
That's the jump. Very good. That's called the jump discontinuity. Actually, a jump or without bounds, whichever way you want. Now, one more thing. As x approaches negative infinity, so here I am at my negative infinity, I get large, smaller and smaller, smaller out there. What y value am I approaching? 0. Because my rule is take the largest exponent in the numerator, the largest in the denominator, and if it's smaller, I approach 0. Same thing as my horizontal asymptote. So didn't that kind of tie this together a little bit? Just a little bit? Just a little bit. Okay. Alright. I was kind of hoping that it would tie together a little bit for you. Alright. Let's go back to the rest. The rest kind of should go a little bit smoother. We'll get stuck one day and not move. Alright. So here we are here. We're kind of back to just regular ones. So I want to know, as x approaches 3, so I try to plug 3 in. 3 squared is 9, minus 3 is 6, whoops, I get a 0. So in order to get that out of there, I factor and reduce. So I factor my numerator, I factor my denominator, and that's the point of discontinuity that I could take out. So my reduced function, I now can plug the 3 into, and I can find where my limit is. Is it okay? This one is always a nice one. For which value in the figure does the limit exist? So at A, here's A. Is there a limit at A? Do they reach the same point, those two pieces of graphs? No. There's a without bounds. I've got an asymptote here. No. No limit exists. So this is one of them. Does the limit exist? Okay. No limit exists here. At B, nope, this is your jump. There's no way I'm going to connect those. At C, does the limit exist? Do they approach the same point? Yes.
So what's that called again? The limit exists, but it's a point of
Discontinuity. And we call this a removable point of discontinuity. Because if I can come to the same y value from either side, I consider it like I could fill it in and just keep continuing. And at D, I'm a vertical asymptote. It just bounces off that. Again, if you graph this, if you factor it, does this point, what is this function? I kind of tied this into, I didn't put a limit on it, I kind of tied it into what we did before. So we factored and we reduced, and we said whenever we take out a point here, this is our point of discontinuity. This is what we did before, in the beginning of the year. So then we plugged in, and we could figure that that was your point of discontinuity. You could graph it and see what it looks like graphically. You probably should. That should tell you if it has any jumps or horizontal tangent. We don't even use that. Let's graph this guy. The graph might be better to tell you what it looks like. So let's graph this. a graph and we're going to see. You have an asymptote, so you have a place without bounds here. An infinite discontinuity? No. But you have a point of discontinuity because you can't see it there. It would be at your 1 because that's where your domain restriction is, in your 1. And over here where x is 1, you really can't see it, so that's your removable point. Horizontal asymptote, I'm not really sure we know what to call it that. That would be like your y equals 0. No. And we call this without bounds. So we can tell from that. Again, just another limit one. As x approaches 2, we can plug a 2 in there. A direct substitution into there gives us your limit. And the last one, right? At a, does it have a limit? No, no limit.
Can you just go back up to the 6?
Yep. 6, we can plug it in directly. If you can plug it in directly, it has a limit. Yes.